Welcome to the next session of numerical simulation with neuroscience for engineers. In the earlier session, we talked about different biomedical applications which can be used so it's a broad range of applications that we studied. Now we want to focus specifically on electrical stimulation of brain. So here what you see over here is the brain or the complete head over here along with the skull and the tissue, and we are going to provide a stimulation at a particular region. So this is the place where we are going to give the stimulation, and this is the ground where we are going to withdraw the stimulation. In an actual example or in an actual prototype, there is not just a single stimulation, but there is an arrangement of various positions of the stimulation. But in our example, we are going to start with simple. So we are going to only use this as a stimulation area and this as a ground region. So let us see how can you do that in COMSOL. So again, the stimulation could be various. So you can start with DC, that is a kind of a DC signal that you can give a certain maybe a 10 millivolts or so, or you can do a frequency domain, that is a certain frequencies you can stimulate with, or you can do a time domain simulation, that is you can give a certain impulse or a kind of a Gaussian impulse, a Gaussian pulse, a very short duration of time, to see how the stimulation is going to affect the tissues within the brain. Okay, so we are going to start with the DC and see how you can do a DC stimulation first, and the approach to our final frequency domain and time domains are on the similar lines. So let me go and start the stimulation. So this is the first thing that you see once you open COMSOL. You just need to go to File, New, and then there are two options. One of them is Model Wizard, and this is the best thing to use the Model Wizard instead of going to blank model. So once you click on Model Wizard, there are different options of dimensions that you can choose from. For example, you can choose a 3D simulation, you can do a 2D axis symmetry, you can do a 2D, a 1D axis symmetry, 1D or 0D. Our simulation that you can see over here is a 3D simulation. Okay, so we are going to choose a 3D dimension, 3 dimension. So once you select the dimension, it's asking to select the physics. So over here, coming back to this figure over here, you can see that we are going to give voltage as an excitation or current per se. So the physics that we are going to solve is the flow of current within the tissue, and this solve requires only the, if you go into the AC/DC module and you go into the electrical fields and current, and there is option known as electrical current interface. So this is the only interface that is required in this case. Having said that, there are also other physics that you may be interested at a later point. So I am just showing you all these modules. So as of now, I will just go to electric currents and I click on add and I click on study. Then the tool is asking me of which kind of study that I want to perform, whether you want to do a frequency domain study, that is a harmonic as an input, or it's a stationary study, or it would be a stationary means a direct current, that is a DC study, or you can also see it as a steady state study, that is at time t equal to infinity what it would be, or I can do a time dependent study where I need to mention the time scales of the model. There are also different options such as small signal analysis, that is you can have both a DC bias along with the frequency domain signal, and you can do a sweep, and there are different like eigen frequency analysis, but we are not interested to do those as of now. We are interested to do only steady state analysis, that is a DC analysis, in case of a static analysis. So I just select stationary and click on done. So that's it. Now I come to the main page or main interface of COMSOL multiphysics. So what you see on the left side is the model builder, and the approach in the model builder is from top to bottom. So what you see over here is the first you make the geometry, then you add the materials, then you apply appropriate physics conditions, then you mesh the geometry, and then you perform a kind of analysis, let it be a stationary analysis or a frequency domain analysis or a time domain analysis, and then finally you post process the results. So the approach that you see is from top to bottom in the model builder section. The top section is the ribbon pane that you see over here in the top, and the approach in the ribbon pane is also the same, that you first make the geometry, then add the materials, apply appropriate boundary conditions, mesh the geometry, perform the study, and finally post process the results. There is also a developer section over here that you can use to write your own scripts and code and couple it with your model. Okay. So with that, let us begin and build this model. So the first thing is to create the geometry, as you can see over here. To save the time, what I do, I have already created it, and I can just insert that sequence within this model. This structures could also be available easily if you just go and search in the some of the CAD free sources. Such kind of structure of the upper part of the body are easily available. The next is to also import the head body. So this is the head part. So this is first thing I start with importing the structure of the head. So you can see this is the structure of the head, and then this ground is already there over here. So I don't need to add the surface for the ground, but I want to have one more stimulation over somewhere over here. To do that, I can just use the cylinder, for example. Okay, so I will just cylinder and just place the cylinder over here. Okay, there is also an option of wireframe rendering. So the cylinder, you can see that it's a very elongated cylinder which passes through the tissue, but I am interested only to have the intersection of this long cylinder with this tissue. So only that surface is what I want to introduce. So I can use an union and delete the domains. Okay, this is operations that I can perform. So such kind of operations can be performed, and what I finally get is this particular surface, and this particular surface acting as a stimulus, but it's still not acting as stimulus. I have just created this surface as of now. I need to apply appropriate boundary conditions to act it as a stimulation, and this is the ground boundary. So that's it with my geometry part. The next thing is to apply appropriate physics conditions or material conditions to start with. So one way to apply the materials is just right click on the materials, apply materials from library, and here you can see there are a lot of materials available within the library of this tool. So you have bioheat, and there are a lot of biological tissues available over here. Okay, what I am going to do is I am not going to use anyone from here. I am going to use my own, and to do so, we just need to right click on the materials, add a blank material. Okay, you can see that it is already selected this particular domain over here, and the conductivity as 0.5 I just choose. So you can introduce your own conductivity and permittivity. Now I am doing for a DC excitation, but at a later point you might also be interested to do a frequency domain excitation, that is at different frequency you want to excite. In that case, the conductivity as well as the permittivity is not going to be the constant, but it could be a function of the frequency. In that case, you can use an interpolation function. So, you can just right click on the definitions, go ahead in the functions and use an interpolation function, and you can import that text file or data file or .dat file or any other format of the file within this tool, and you can write the name of that interpolation function over here. So, you are done with the material section. So, you applied the appropriate materials, and that is what you see in the blue highlighted domain. The next thing is to apply appropriate physics conditions. To do so, what I do, I just right click on electric currents, and you can see the complete list of domain conditions. So, you can see this is a cylinder which is fully filled with blue color. So, this is a blue fully filled cylinder which represents domain conditions, and this is cylinders which are half filled which represents boundary conditions. Okay. So, we actually need to do a boundary conditions, not the domain condition as of now. So, there are different ways to excite. It could be electric potential, or it can do a normal current density, boundary current source, or terminal. You have floating potential where you want to withdraw the potential, that could also be possible. This is the main source condition. So, what I will do is I will choose the electric potential. Okay. If you want, you can use terminal also. So, terminal is a more robust boundary condition. So, just choose terminal, and I go ahead and select this particular boundary over here. So, you can see if I remove the wireframe rendering, that I have selected this particular region to stimulate my this particular region. Yeah. Now, there are different types of excitation that I can use, whether it is current or voltage or through an external circuit or a power. As of now, I will use voltage excitation, and I mark it as V naught, for example, and this V naught is showing an unknown variable as of now. I can go into the parameter section and mark V naught as maybe 10 millivolts. Okay. So, I am marking it as V naught. I also want to see how much current is being withdrawn from this region. So, that is what also is feasible if I define terminal 1 condition. If I define it as electric potential condition, then I cannot quantify the current. So, this is the more robust, as what I was that is what I was saying earlier. So, terminal is a more robust boundary condition. I apply a potential over here. Now, I need to apply ground in the top. So, how do I do it? I just right click on the electrical current interface, and I choose the ground boundary condition and apply on the top of the head. So, this actually acts as a ground condition. So, you can see the equation over here, that is the voltage is 0. Okay. So, this particular localized region of the head actually works as a ground. The next thing is the meshing. So, if I go to the mesh over here and I click on build all, you can see that this particular geometry has been meshed. Meshing plays a very important role because the geometry that you created is not going to go and be solved in a set of equations in the solvers, but it is the mesh which is going to be get solved within the by the solvers. So, here you can see that if you go and make it extremely coarse mesh, you can see that it actually deforms the structure or surface of the head, and very poor meshing is being shown over here. You can see even the nose is not that good. Okay. So, you can either go for a normal mesh, or even little bit finer, or based upon the physics. For example, you sometimes need to mesh the geometry. Okay. For example, you are looking for very high frequencies in cables. Okay, so then there is an effect of skin effect. Okay, so in that case you might need to do a boundary layer mesh. If you are working on a very high frequency like optics or RF applications, in that case you need to resolve the wave that is propagating through the tissue. So in that case you need to do a 1/5 of the operating wavelength over the refractive index of the tissues, or if it is not a refractive index, then if you have permittivity, then it would be the denominator would be square root of the permittivity. So it depends on the physics as well. As of now, the electric currents is not that like gets affected by the mesh, but the geometry should at least not be getting affected. The next is to perform the type of study. So as of now, as I have discussed earlier, this is a DC stimulation. So I just use my stationary analysis and I click on compute. So here you can see what is happening over here. So what the first plot that you that is getting generated is an electric potential plot. Okay, so it shows how the current or the voltage is being varying from this place to this place. But I want to see this plot somewhere in this plane. So there are different ways to create more intuitive images. One of them would be to use data sets. So I want to create a cut plane, for example. So just right click on the data set, I create a cut plane and I want it in the ZX plane. So along this plane over here. So I choose the study one solution in the data set. This is the main data set which has all the solutions. Now I want to make a subset of this data set into specific regions. So I want to choose, for example, ZX plane, and if I click on 0, then it would be y coordinate 0. So this is the place that the results are going to get evaluated. But I don't want it to be over here, but little bit on the right side, because I want it to get overlapped with this region. So for example, I will just try to make it a little more negative. Yeah. So now you can see that it is overlapping nicely with the stimulation. Okay, I give stimulation over here, and this is the ground. Looks good. So now what I am going to do is I want to evaluate the electric currents, potential, all of them in this plane, the red plane that you see over here, 2D plane. So results would also be 2D. To plot the 2D results, you can just right click on the results and there is the option of 2D plot group. Yeah, so now you can see this is actually having a rotation of 90 degrees. So instead of ZX plane, I can use XZ plane. Okay, which is now makes it more straight, kind of a vertical. Now in this 2D plot group, what do I need to plot? There are a lot of ways that you want to plot, but the first thing that you should think to yourself is, what do you want to plot? For example, if it is a voltage plot that you want to perform, then it is scalar quantity, and scalar quantity could be plotted using surface plots. But if you want to model something, or you want to plot something like currents, electric currents, which are inherently vector quantities, so in that case you would need to require a arrow surface plot. Okay, so let me go and choose the surface plot to start with, and this is the voltage, and I make it as a millivolts because this is what is going to be. Okay, so you can see how the voltage is varying from here to here. Okay. You can also plot the electrical field. Okay. Just right click on the 2D plot group, add one more surface plot, and you can just search. So this is an if you just come over here, it's a replace expression section over here. Just search for electric field. So with this you can get an option of ec.norm e. This ec.norm e is the electrical field. You can also plot the individual electrical field components, that is x, y and z components. But as of now I am going to plot the normalized electrical field, that is square root of the x square plus y square plus z square quantity. I can make it a different color table. For example, I can make it aurora australis and plot it. Okay, so there are two images which are getting overlapped, so I will just disable my first surface plot. Okay, and perhaps I will use some other different kinds of okay. So now for example, I want to see how the electrical field is kind of propagating between these two. Okay, so here you can see somewhat that the electrical field is high somewhere over here and here, but I am not visualizing that clear. So I can just play around with the data range. Okay, so I can just play around with that perhaps from maximum to 1, and I can just make it a little bit less. I just keep on going a little bit less. Okay. So here you can see if I have something like this. Okay. So this is the region of electrical field which is at least more than 0.02 volt per meter. I can just choose any other color also. Okay. Okay, for example, this one is looks better. So you can see this is the electrical field surface plot. Definitely it will be more on this edges of the stimulation because of the discontinuity. Now I want to also see the flow of the electrical field. To do that, I just right click on the 2D plot group and I click on, I can use a arrow surface plot, and again by default it is showing the current. Okay, so let me start with the current, not a problem. So I want to visualize the electrical currents within this profile over here. So how do I do that? It's already over here. Color is red. Just click on plot. Okay, so here you can see you can visualize the current that is flowing from here and it's coming over here, but it's not that nice. So what I can do is, instead of proportional, I can just choose logarithmic. Okay, so logarithmic plot is what you can see over here. I can increase the number of grid points or the number of arrows. You can see over here. I can choose some other colors, for example, perhaps white color. Okay. Yeah, so now this is looks kind of a better image to see how the stimulation is actually occurring, how much the flow of current is happening over here. Okay. You can also give you can also plot the electrical field instead of the current. So you can just change this variable over here and just search for electric field. And just start searching for electric field and you will see these variables over here, Ex, Ey, Ez, and just double click on them and click on plot. And what you will see is this very much similar to the current because they are kind of proportional, but the value would be different. So what I do, I just right click on arrow surface and I click on color expression, and here I can just write ec.norm e and I plot. So here you can see that I'm not just having this electrical field arrows, but along also with the colors. Okay, so let me just check which would be the good color to visualize. Yeah, perhaps this one. So here you can visualize that the electrical field is significantly high, because this is this legend over here, significantly high over this region over here, and as you go over here it's little bit high, but in the center what are the electrical fields comprising of. You can also increase the number of arrows, maybe perhaps 45 and 45. Okay, and that gives you a better picture of how the flow of current is happening. Okay, so you can also see that the current is also flowing in the these regions also. Okay, okay, that's good. So this is how you can actually visualize the electrical currents, also the electrical field along with it. You can also perform not just the DC analysis that I was discussing some time back, but you can also do a frequency domain analysis. To do that, it's very simple. You just need to go to study, add study, and I can just do a frequency domain analysis. Just double click on it, and then it just asks me about the frequency. So for example, my input frequency is around 1 kilohertz. So my input is not just V0 now, that is V0 which is defined over here, this 10 millivolts, but it's now 10 millivolts into sine omega t, where omega is 2 pi f and f is 1 kilohertz. Okay, and I click on compute. So that's how simple it is. Once you set up the model, you just need to add different studies and you can get the results. Now in the cut plane, instead of study 1, which is the stationary analysis or the DC analysis, I will just go ahead and choose the study 2, that is a frequency domain analysis. In this, I can now go and see over here, it's showing me a cross over here because it is studying something else. So yeah, in this, what we are doing right now is the frequency domain analysis, and the good part of this tool is that with this frequency domain analysis you can do a phase dependent animation. What do I mean by that is, if I for example create a surface plot and I create maybe a 45 logarithmic, yeah, perhaps a white color, yeah. So you see the current flow as well as the electric potential. Now the good part of this tool is that it does it solves the frequency domain by solving for different phases. So it's still a stationary analysis, but it solves at different phases. Okay, so phase dependent animation is also possible. So how do I run that? How do I create an animation? How do I save that animation and use it in my presentation? So it's very simple. So I just go to animation, go to player, and over here instead of stored solution, I just use the dynamic data extension and I click on play. So here you can see how this animation is playing out, and I want to play it for infinite time, forever perhaps. So you can see how the stimulation is being performed. So in the if as it is a sine wave, it has 2 cycles. The first cycle is a positive cycle, second cycle is a negative cycle. So over here you can see that in the positive cycles the current is flowing from here to here, and in the negative cycle it is flowing from top to the right side. Okay. So here you can see how the stimulation is happening in animation. Now the good part is that you can also save this animation in the form of a file and use it in your PowerPoint. So how do I do that? So and this is very good for showing the results, showing this in a presentation, for example. So instead of target, I can use a file, and I can use my, and that's it, I guess. Okay. Yeah. So I will just keep everything as the default as of now. Frames per second, I can just make it 5, little bit slow. So FD stands for frequency domain stimulation. So it has now created that animation, so it's almost creating this animation. So meanwhile what I can do is I can just go add a new slide, for example, and once it is created I can just pick and drop that animation into my presentation, and this is how easy it is. It is created that animation. Now I just go to this animation, just drag and drop over here, that's it, and I can just go to my full screen and you can see this animation over here. Okay, so it has 2 cycles. Your first cycle, this is the first cycle is this one, it goes from here to here, and second cycle you can see it goes from here to these positions. Okay. So that's it with this session. The next session we'll talk about multiphysics analysis of how you can couple this current that is flowing into the rise in temperature within this tissue, and what are the things that we need to account for this multiphysics analysis in that case. Thank you.